All right. So my name is Mario Arduz. I am working for the LinkedIn AI team. And today for the session of the paper club, I'm going to present the paper Survival of Patients with Primary Brain Tumors, Comparison of Two Statistical Approaches. I think my main motivation to review this paper was to learn learn the topic of survival analysis. I was completely not familiar with it, so also this presentation will focus on some of the main methods of survival analysis. It's going to be introductory. And yeah, like this topic, it's interesting for us because we can apply it to churn analysis, and perhaps this is going to be good to know. And other reason why is because the book of Introduction to Statistical Learning had a new release earlier this month with some Python application. And I just wanted to check it out, and I think this was also a good reason to do it because this is some data that they have at the chapter where they explain survival analysis. So beginning with a description of the paper, this is a medical type of paper where they are going to analyze the application of radiation, different radiation methods in treating brain tumors. The main types of these radiation methods are single or fractionated doses. Single one, I think it's stronger, and the other one perhaps is going to be perhaps the same amount of radiation, but in several instances. And they have also some other characteristics that they want to relate with some outcomes that they can observe in their patients. The characteristics can be the diagnosis that they have with regards of how malign the tumor is, the tumor volume, the location of the tumor, and other characteristics such as age, sex, and health condition of the patient. They are going to try to estimate for one side the probability of a patient survival over time. So it would be what would be the probability for a patient to be alive in the next year, in the next 2 years. And they are also going to try to relate these probabilities in a way that they can explain them with some of the characteristics that they have, the characteristics of the patients and of the characteristics of the tumors. Something that I think it was interesting to see is that they only have like 88 patients that were examined around 7 years. I think this is really, really hard to draw conclusions if we don't really see the context of it. Surely it's difficult to track all of this information for the patients. But having 88 data points, I also think it poses some challenges on the models that you want to apply. Perhaps some of the assumptions that you are getting or that you are having with some of your approaches are not going to be valid. And I think this is also one of the drivers that they are going to, not drivers, but reasons that they are going to have not to use the regular approaches of survival analysis, but trying also different type of methods in analyzing this information. But the main thing of why this has to be done with other type of analysis, that it's survival analysis and not just like a regular regression, is because there is some sensory information in the data. Sensory information would mean that that we don't really observe the true survival time of all the patients. Let's say that we begin the study and the information that it's true, that we only see as true, is for the patients that die before the study ends. But there are going to be some patients that are going to be alive for the time that it's after the end of the study. And for this, we are going to see kind of the information that is cropped. I will try to just use a pointer. Okay, here it is. Okay. Can you see the pointer? Mateus, I don't know if you just...
Yes.
Okay, good.
Yeah.
So there are going to be some, like these red lines are going to represent the patients where we indeed see the true survival time. But there are going to be these blue lines that represent instances where we don't really see the true survival time, either because the examination period has ended, or because they are going to drop in the middle of the study. So if we think that, let's say, we want to calculate what would be the survival time that is greater than 20 months, we can just calculate this in a ratio of the people that survive in regards of the other ones, because we would be underestimating this number. There are going to be some points like this that we don't know if they are alive or not after 20 months, or perhaps some of the points around here that we are not going to have like 20 months of information, but they were alive until the end of the study. So this topic of having sensory data, it's the one that motivates other types of applications that give origin to the to survival analysis. And in survival analysis, there would be let's say that two types of main functions, or perhaps the ones that can introduce this type of topic. One would be the survival function, and one that is the conditional hazard function. The survival function is just the question of what would be the probability of for a patient to be alive after a certain time, and the conditional hazard function would be trying to estimate the risk of dying, or trying to estimate the risk of dying in terms of some of the characteristics that that these patients have. They are pretty connected. We can think of the conditional hazard function just like the velocity in which this risk increases or decreases, like the derivative. And yeah, the second step would be trying to model it in terms of other variables, whereas the first one is just trying to capture this or model this function, this behavior in terms of time, without using any other characteristics. And what the paper is proposing in here is have these estimations of the conditional hazard function, but with a kernel, with a nonparametric approach. They are not going to use for instance, in the case of the conditional hazard function, a parametric form. They are going to estimate it with a kernel. And with the estimations of the conditional hazard functions, they are going to calculate the survival function. Just because they are pretty, they are interconnected in a functional form, right? One would be the derivative of the other one, let's say. So yeah, this is going to be the main approach of the paper, trying to propose these new alternatives in trying to estimate the conditional hazard function and getting some conclusions out of the information that they get with this review of 88 patients in 7 years. So here, just to talk a little bit of some of the variables that we are going to see, especially in the calculation of the survival function. Yeah, repeat it again that we are only going to look at a variable, random variable, that is going to be either the minimum of the true value or the censored value. The censored value would be when the patient is still alive until the end of the study, or if the patient drops in the middle of the examination. And we are setting this delta parameter to 1 if we indeed see the true outcome, and 0 if we don't see it. And these other variables here are going to be mostly important only for the next calculation, but we can already explain them. How are we going to tackle the calculation of the survival function? We are going to make some assumptions. First, we are going to divide all the possible times of death in different steps D. We are going to order them, and we are going to assign the patients that we know that were alive at this times D. This is going to be per K. But it would refer to one step back just because it's the patients at risk of dying. How many are going to be the patients at risk of dying at time D2? Are going to be the patients that were alive at time D1. And the number of patients that they die at at the time, they are going to be represented by this Q sub k. So I guess this is an interesting part in terms of the derivation of how they can estimate this survival function. Is that okay? They are going to try to estimate this probability. What is the probability that survival time is greater than this time G sub k? They are going to apply conditional probability to this, and they are going to use the conditions based on a true time that is greater than d sub k minus 1. And the complement of this information, that would be that t is lower or equal than dk minus 1. This part is going to be canceled out just because if a patient true time or survival it's lower or equal than dk minus 1, they are not going to be alive in dk, right? They have died before. So we don't consider this term, and we are going to have this remaining part of the extension of this conditional probability. And what I guess it's also nice is that they are going to apply like a recursive approach to this. Because here we have the probability that a patient will be alive after decay. We have that this is a function of what is the probability that the patient would be alive after the period decay minus 1, and decay minus 1 can be a function of decay minus 2, and so on. So they are going to apply something like like a recursive way of solving this problem, and they are going to estimate this probability over here as the ratio of the risk that the patients that were alive in a previous time step, how many of them died at the next time step, having this as a ratio, and then multiplying it for the next instances that they have. So this would be an example of this calculation. They are going to begin with the first step. How many of them were alive at the previous step? They are going to be 5 patients. That's why we have 5 at the denominator. And then how many of them died at this step? The yellow points are going to represent the ones that we indeed see their true value. So it's going to be just 1 that they died, 5 minus 1, it's going to be 4, 4 divided by 5. This is going to be the estimate at this time. They are going to repeat the process for all the instances where they see the true values. Let's say at this instance, how many of them were alive at the previous before? It's going to be only 3, because here the data it's censored. So it's just going to be the 3 that are above. 1 that dies, and then they repeat the same procedure. They are going to subtract the number of people that died in the next step and dividing it by the ones that were truly alive at the previous one. And with this, we are going to get something like a step function like this that is going to provide us an estimate of what would be the probability of a person to be alive after this period of time. They are only going to consider the censoring data when it's present. Like they are not going to consider it in here because they don't know if they are alive or not. But at the first, or let's say at the 0 point in time, they are going to consider because they were alive. And then they are just going to multiply these numbers, and they are going to have this step function. This would be something this is like the graph that they have for the survival function of this analysis. And this would be one of the main questions that they would be trying to ask. These are going to be the probabilities for a given patient to be alive after this number of months. And the second, let's say, base function not base function, like the second important concept in survival analysis that you're also taking as reference, because they are not using, I am not talking about the kernel yet, is the Cox proportional model. In this case, they are going to try to model the hazard function as it's in here. It would be like the derivative of the survival function divided by the value of the survival function. This is as the derivative. Let's say it's going to be negative. They put it in negative so they can talk about a positive hazard. They are going to model it in terms of a functional form of some variables. And the functional form is going to be this exponential one. But they are also adding some function of the time, some risk with regards of the time, that they are not assuming any type of function just because they are going to cancel it at the end. They are going to cancel it because once that they have like this hazard function for a combination of variables, they are going to say, okay, what would be the total hazard of this type of expression? That's why here we are summarizing for all the cases that we indeed see that it was a true value before this time, and then they are going to cancel out this like base risk, or yeah, like these base risks that they don't know the functional form. What I would like to just make more clear in this explanation is that we are assuming a functional form of relating some of the characteristics of the patient to the hazard function, and in the way that they are trying to do this, it's also relating it with a base risk that it's going to be dependent on the on time, and they are going to cancel it when they are summing all of the hazard functions of the patient, so they don't need to think about what is going to be the function of this base risk. And then when they are going to have only these parameters that they are going to try to estimate, they are going to do it by partial likelihood, because they would pretty much have all the information that they want. But having this functional form is also going to impose some type of assumptions. In this case, the influence, these are two different variables, and these variables are thought to be dichotomic. They are only going to have a value of 0 and 1. They are going to have like they are going to be pretty well separated, let's say. So the effect of having one variable and the other would only mean like a vertical displacement of the line. Perhaps like in a logarithmic scale, it will, the distance between them, it would be the same. But I guess the main idea is that the lines are not going to cross. The hazards are not going to cross, which would be a different situation if our data would show us this type of relationship, right? Where there is going to be some parts where one variable is going to have more hazard than the other, but if we progress in time, that this relation will reverse, because it is in this case, right? So there is like a bigger survival probability for when the variable, let's say, it's set to green, but this only happens when, let's say, that the threshold it's lower than, let's say, 1.4, and if it's greater than 1.4, then when X is set to black, it's going to have a greater survival probability if we compare it with when X is set to green. So the assumptions that we are going to have or impose in this model are definitely going to have an impact in the way that we are going to try to model these characteristics. So this is also something that they mention. It's important because sometimes these assumptions are not going to hold true. Then moving to the kernel application of it, they are just going to try to weight some of the observations that they see with neighboring observations with regards of time and also with regards of the covariates. At the first situation here, we only see that there is a kernel being applied with regards of time, and here we see that the kernel is applied both to time and the covariate. In this second case would be the conditional hazard function, because they're going to try to model the hazard function in terms of the variables that they have. And the comparisons that I'm going to show next are going to focus on these ones, because I think it's more interesting to go a little bit more about the assumption of the exponential influence of the covariates in the outcome. And yeah, in the situation where they are modeling just the survival function, it's not as interesting because we don't see really much, like really big difference. But even in the case where we are going to try to model the hazards in terms of, let's say, age, I guess in this situation, we also don't see like a big difference. Here would be at the middle, or let's begin by the left. At the left, it's just like the death rate, plotting the death rate over a combination of age and let's say the survival time, and where age is a characteristics of all the patients. And in the middle and the right, there are the estimations of, the middle would be a kernel estimation, and the right one would be a Cox total hazard estimation. In the case of the kernel, we can see that we are kind of capturing this type of relation, but that in general we would see a pretty much same behavior across the rest of, let's say, the grid of age and time. So they would be a bit similar. The author says, besides this part where we are kind of seeing an increase in the hazard of this combination of low years and after passing some time in months, the relation is pretty similar. So we are going to prefer the Cox model, because under the Cox model, we can also have some more explainability because of the parametric representation of the hazard. With this, it's going to be more easy to do some testing. It's going to be more easy to set some influences, whereas on the kernel, it's a bit more difficult to do this type of estimations, right? So in this case, they say, okay, we can prefer the Cox model because we are not going to stress the assumption of the exponential relation between our covariates and the results of the hazard function. Whereas in the case of analyzing the volume of the tumors that is represented by this GTB, here there are different types of slopes in different survival times. So we can see also in the data that here the death rate increases, then it decreases, and then it decreases again. And this is somewhat shown with the use of the kernel. But if we are going to try to apply the Cox representation to this, it's basically going to just concentrate the hazard over this area and then decrease it in the rest of the combination of these variables, right? So in this case, they say, okay, perhaps the representation or the assumption of exponential dependence is not good, so we are going to try to use the kernel estimation, because we can see that there are going to be different types of increases and decreases in the hazard function, depending on the combination that we have on these variables. And then what they will also follow in this case is that since we are going to have this behavior that it's not completely described as an exponential function, we can group patients that have similar types of risk, and they are not going to be completely determined by the covariate. So what I am trying to explain here is this: like here, the risk is going to be concentrated in this region of the combination of these variables. So perhaps like lower time, a higher volume is going to have high risk. But in this case, not. Like we are going to have some part of high risk that is going to be only after passing some time with some value of the volume in here. So the region across here, around here, then we are not going to have some risk. There's going to be a decrease in the hazard risk, and then it's going to be another increase in the hazard risk. And these two segments of the information will have a similar risk, so we can treat them together. Despite that the combination is not as delimited as in this case. I'm not sure if these explanations went well, but the idea would be to group patients according to their the risk, and not really focusing on just moving a threshold, but focusing on areas depending on the result that they have of this function. So yeah, like some final remarks of this paper. I think, yeah, I was kind of going ahead with the first one. trying to divide patients in terms of their similar risk, and this can be this will be really dependent on the estimation of what risk is. But I guess with these two examples, it really depends on checking the assumptions of the model that you want to have. And yeah, this kernel estimation that they are proposing, it's a good alternative if the assumption of exponential dependence is not called. And I guess takeaways that are really general, really general, because they can always apply to any type of analysis that we are doing, is that we have to be really aware of the assumptions and limitations of the models that we are using. And that perhaps the increasing flexibility also comes with a cost. I guess in the case of age, I don't know if the relation would be still like well represented with this increase that we see here. Perhaps, I don't know. There is going to be also some influence on some noise over here. So the increasing flexibility is also going to adapt to some of the noise. But yeah, like these are like really general considerations that we always have, and I guess it's interesting to see it in this case. I guess it's also a really challenging to have like conclusions drawn from 88 points of data, but it's also interesting to see the different approaches that they are trying to have to track conclusions. So yeah, this is what I have prepared, and if you have comments or questions, we can have them ready.